Um, so, like usually when your system crash or a system hangs, what do? Reboot the system, restart कर देते हैं. But what about systems which are not reachable by humans? So for such systems, we have something called watchdog timers. It is an electronic timer which is used to detect and recover from computer malfunctions. So how it works is basically the entire main function is run in a continuous loop, and this acts as the watchdog timer acts as a timer and it counts down. So before the countdown gets over, the system has to send a signal. It can be in the form of an instruction or some signal to the timer. It is called kicking the watchdog. It is so if the watchdog gets this instruction, then that means that the entire system is functioning normally. So it will reset the timer again. But in case it does not get this instruction, it times out and the entire system stops. So the timeout can be in the form of an interrupt or a processor reset or a power cycling. This is used in various embedded systems and in space probes also. So there is this example. So there was this Clementine spacecraft which was which was in the skies during 1994. So एक asteroid पे भेजा था, and in 6 months there was a floating point error program में. उसके कारण पूरा program crash हो गया. And the software started running the thrusters which it wasn't supposed to. So by the time the engineers were able to send a hardware reset, the entire fuel was complete और सिस्टम को पूरा को अबॉलिश करना पड़ा और स्पेसक्राफ्ट वापस आ गई. बट एट द सेम टाइम उसी साल में पाथ फाइंडर करके एक स्पेसक्राफ्ट गया था मार्स पे, उसमें भी सेम इश्यू हुआ, बट उसमें देयर वाज अ वॉचडॉग टाइमर प्रेजेंट. तो दे वर एबल टू गिव एन इंटरप्ट, send a software patcher, and the mission was successful और वो मार्स पहुंच गया.
Thank you. Anyone used Arduino before? So if you've used Arduino, you might have heard about the watchdog timer now. So especially it's used for one of the utilities of watchdog timer is when you want to sample data. So you put the Arduino in a sleep state and it wakes up only to sample and then send the data or store the data. That can be done using the watchdog timer. Okay. Here's an histogram of the quiz, and if you're on the left side, so you really need to pull up your socks. I think it was a reasonably easy quiz, but I'm happy that majority of us have done good. So very good percentage of the population has more than 20 on 25 marks. Some other quick administrative announcements. So we'll be completing virtualization by this week. By virtualization, I mean virtualization of CPU and virtualization of memory. So it's roughly the halfway point of the course. And like after each module, we'll have a homework and a quiz. So the homework should be coming soon in next 3 or 4 days. And it has to be followed by a quiz on next Thursday, 13th of September. So be prepared for it. In the last few lectures, I've seen that most of you are not very well prepared, are not revising. So if that trend continues, do expect a surprise. Again, +2, -0, 1 and above 100 marks. Yeah, so I want you to have another lab or so, and that lab will give you a better idea of the kind of projects that you can do. So again, I'm going to revise because I think this is the most important set of slides. Conceptually, the most important set of bits. So you may not get the in-depth understanding, but at least the big picture should be clear. I'm going to ask again people. So base and bounds. What are the pros? Sahit?
It uses less number of registers.
Okay, so it's uses fairly less number of hardware registers, fairly quick to register. Cons, Ayush? So it requires contiguous block of memory which leads to fragmentation. We improve this using segmentation. Naman, what are the pros of segmentation?
So it reduces some sort of fragmentation due to segmenting the blocks.
Okay, so it reduces the requirement of total contiguous block of memory, and it's still relatively quick. The cons, Nitiksha. So it still requires contiguous block of memory, which can lead to internal and maybe even external fragmentation. So we moved from segmentation to paging, but before that we looked at, we had a thought experiment that why not map single byte of the BA to a single byte of the PA. That's problematic because that leads to huge overhead in terms of the page table requirements. So we moved to a more realistic solution, which is paging. So the pros of paging are
Very less segmentation.
segmentation or fragmentation.
Fragmentation.
Okay, the probability of fragmentation is greatly reduced. Why that's so?
Because each byte is particular.
No, so you're not mapping a byte
Segment.
each page.
Each.
Okay, and what is the typical page size? 40. So it reduces the chances of segmentation, but cons, it's still, it becomes slow because you have a lot more memory accesses. You need to go to the page table to get the corresponding entry, then you need to fetch the corresponding physical addresses. We move to paging plus TLB, Monarch. Yeah. Why is it good? What are the pros of paging plus TLB?
Because it will go to a sort of cache.
So why is that good?
So it will improve the time.
So it reduces the accesses to the physical memory RAM. And why is cache quicker than the RAM?
Because it will not access the.
So it doesn't require access to a slower memory. Cache is present either in the memory unit or the cache is present alongside the CPUs. It's fairly quick. Okay, so what limitations do still exist at this point, Monica? Suppose what are these limitations that still exist at this point of time for paging? So we've improved the speed. What else do we need to improve upon? So you need to look at the cons of paging and then answer. So what are the cons of paging? Let's read them out. Okay, so what is TLB improving upon?
Lot of memory accesses and slow.
Okay, then what else is there?
So linear page table like.
Memory overhead. So that's how I want you to remember this entire slide, that you improve upon the weakness of one approach in the next approach. So you look at the cons, slow, a lot of memory accesses, you improve by using a TLB, memory overhead, you improve by using the set of techniques that we just started last time. Okay, so we want to reduce the memory overhead of paging. We start with, let's say, an example 32-bit address space, 4K pages. 4K pages means 12 bits. We're using 12 bits for the offset. That means we have 20 bits remaining. 20 bits remaining means that we have VPN of 2 raised to the power 20. So, and if we are using 4 bytes for translation, or for each page table entry, if we're using 4 bytes, that amounts to 4 MB per process, which is huge. This is what we're trying to reduce, the memory overhead. So we're not now optimizing the physical address space. We're optimizing the space required by the paging itself. So we want to reduce the amount of overhead that paging itself has. The first trivial solution that we took was if we decrease the size of the virtual address space. Why is this bad, Ayush?
Because the whole of the program might not fit in the least virtual address.
And this is in some sense defeating the purpose of memory virtualization, where we said, in some sense we have infinite amount of memory available, physical memory available, which is not true, but we don't want to reduce the virtual address space. Many programs won't even be able to run. Okay, so if we do something else, if we increase the page size, Devanuj, why is it good? Why is it bad?
Increasing the page size, the number of translation reduces.
Okay, good.
Just the overhead decreases, but still, since we you're increasing the page size, the issue of fragmentation of
Good, excellent. So we always have this trade-off that if we increase the page size, the number of transitions decreases. So the memory overhead of paging reduces, but then the fragmentation will increase since they can be smaller code segments or smaller pages that you want to fit in. Good. So let's look at this picture again. So let's say this is a virtual address space, and that is a physical address space. We have code, heap, and stack, and there's a lot of empty spaces in between. So currently, what is happening is that we are allocating this entire contiguous block as so. This is how a page table would look like. So we have this contiguous block which corresponds to virtual address, VPN to PFN mapping, and we have a valid bit whether the transition is valid or not. Now there are a lot of empty entries in this page table. So this is what we're trying to optimize. Reduce these entries or the requirement to store all of this entire page table contiguously. All of this is wasted. Linear page table, what is the number of entries required? Smith? This is 16 entries. So how many entries do we require in linear page table? This is a linear page table. This has 16 entries. How many entries do we require to store? Sorry? Like how many entries does this linear page table have? That 4 valid entries, but how many do you need to store? Or how many, what is the maximum, what is the size of the page table? That is still 16 entries. But even though you might not have allocated those entries, but you still need to have those entries. The potential has, they still have a potential to be addressed. So you have 16 entries, 4 of them are being used, 12 are not being unused. That is the amount of wastage in a linear page table. Lookup is going to be order of 1 because you know the direct mapping. Space is 16 into size of each page table entry. Let's say it was 4 bytes, so 64 bytes. It requires that entire space. Yeah, last. So, what sparse data structure can be used to reduce this memory requirement? Yeah. Addition.
Oh, linked list.
Okay, so we can use a linked list. Why do we use a linked list?
Because then you don't need those entries in the list.
So then we don't need to store all of these entries. Linked list will only contain a list of the present entries. So we convert it to something like the following. This is the BPM corresponding PFN, and we just maintain this 4 elements. Linked list, the advantage is that the lookup is going to be slow, but the space requirement is going to be much lesser. So we require only 4 times the size of each page table. So again, a trade-off happens between the lookup. The lookup has become slower compared to linear page table, but the memory overhead has reduced. Ideally, you would want to have a quick lookup and a small size overhead, but that doesn't happen. So it's always a trade-off. So previously, when we were trying to fill in the holes in the physical address space, we looked at segmentation and we looked at paging. So now what we're trying to do is, can we do the same thing, not on the physical address space, but on the page table? So the idea is that we go back to this page table. So let's say this is a code segment, this is the heap segment, this is the stack segment. Can we create separate page tables for each of these so that you don't have to give a contiguous block of memory to this page table? So the first idea is segmentation plus page tables. So we use different page tables for each heap, stack, code, data, etc. One of the key differentiations between regular page tables is that each page table can now be of a different size. Each table will now have a base and a bounds. What does the base indicate? What does base contain here?
Physical address of the page table.
Good. So it's going to be stored in the MMU. The base and regular segmentation contained the physical address where the segment resided, but in this case, it's going to contain the physical address of the page table for that particular segment. What will the bound contain? Yeah, Udan. Size here corresponds to
Number of entries.
good. Excellent. So size contains the number of valid pages at the end of the page. So let's say we started with a 32-bit virtual address space, and if we have 4 KB pages, so the offset corresponding to 4 KB is going to be 12 bits. 20 bits left, which go to the VPN to raised to power 20 translations. That's humongous amount of page table linear contiguous block that is stored. But now what we said is, let's look at how we can address, how we can figure out which segment is being used and what is the corresponding physical address. So we give 2 bits to this segment, the most significant bits. We have 3 different segments in this case, so 2 bits will suffice. So 2 bits, 12 bits, 14 and 18 bits. So this is how we create different page tables. So let's say this was also valid entry. So for the code page table, we have only 2 entries. Where the base is 0, the bound is 2, we have 2 entries. For heap, we have, let's say the base is 0, 1, 2, 3, 4. The base is 4, bound is 2, we have 2 entries. And for stack, we'll have something else. The direction might also be. But let's not look at that.
So why is heap the bound is 2? It should be 1.
So just imagine this is another entry.
Means in the actual physical address space, we are only allowed to access to 2 pages of memory for the heap.
Sorry.
When bounding the number of translations to only 2 over here.
Right.
So in that we are telling that the actual physical address space for this
At this point of time, we can allocate only 2 pages. But that's
entire 2 pages of memory only to heap.
But let's say we want to increase the heap, then we have to allocate another. We'll have to find another free page, allocate that, increase the bound by 1.
Sir, do you always add an extra invalid page?
Do we always add an extra invalid page?
Yeah, like
Because we are directing it
No,
to
this should have been valid. I just didn't want this table to look too small. No, we never add any extra invalid page.
Sir, what is the lookup time?
What is the lookup time? Yeah, what do you think is the lookup?
It depends on number of segments.
Okay, so we have k segments. So assume that the operation required to look up these, to find the segment is constant. Because that's fairly quick, you can do that in hardware also. So then what's the lookup time? So it's almost the same.
size of
Sorry?
order size of the largest page.
So it's still order 1. Because at that point of time, it's you know the mapping between a VPN and a VFN. It's a contiguous block, so that is why you can just directly jump to that place.
These are linear page tables, right?
These are linear page tables at this point of time. So what you've done is you took that big linear page table, you removed all of these spaces, and you just created smaller page tables. So you have more page tables, smaller size, all these spaces in between are removed. But then what you're doing is you're creating variable size page tables.
Indexing into one of those page tables should take constant time.
Right.
And finding the exact translation inside that page table will take again constant.
So it would have taken non-constant time or linear time if we didn't have a specific ordering or we didn't have that. So we can simply use the fact that we put them in order.
How do we know before time that 2 bits will be suffice to find the correct segment?
So we 2 bits would be sufficient because we have 3 segments. If we
one
had
of the segments is such that what 2 bits did not correspond to the entire segment. Like suppose it went into 0, 0 and 0, 1 and then 1, 0, 0 because the segment is too large.
we did that. So then we'll have to left shift everything and then again use 2 bits. That's one of possible solution. There can be many.
So will there be only one heap page table and one stack page table? Or like a
So
different-
yeah, so currently that's the thing. So you just have again there can be different implementations where you can have list of these. So I think the question he's asking is, let's say if there were breaks in between, or there, if we have a heap segment, and in between that heap segment also we have some spaces, some empty spaces. So do we create a single heap and then again have some internal fragmentation, or do we create multiple of these page tables for heap? Another way to look at it is that for the heap also, for each of these, now instead of creating a linked list for the total page table, you create a linked list within each of these segments. It's getting fairly hairy complicated at this point of time. So the pros of segmentation plus page tables leads to memory savings, because all of the large contiguous wasted spaces need not be allocated. Cons, it uses segmentation, which always comes with a set of cons. It has a certain pattern of address space. Sparsely used segments, like what I was discussing just now. If you have sub-segment internal fragmentation, that also leads to space waste that can be addressed using either linked list or some other data structure. And we also have variable size page tables. So now let's come to the new content for today. We said that we could fulfill the holes either using segmentation or using paging. Segmentation, we have seen some flaws. One of them is we're using variable size page tables. So how can we address that? Fixed size page tables. And if we want to do fixed size page tables, the way we did fixed size small segments in the physical address space was to use paging. The way we can do fixed size page tables for the page table is to use paging. So the key idea is we start with a page table, we break it down into pages or into subsegments. For now, let's break down the page table into pages. And a page directory refers to these pieces. So let's look at a small example. Let's say this is our page table, linear page table. We're using the same page table as before. And it has, again, 1, 2, 3, 4 possible entries, or valid entries. But the total entries are 16. So we're wasting 12 spaces. Let's say that each page table entry corresponds to 4 bytes. And let's say that each page can accommodate 16 bytes. So how many entries can we have in a page? So I'll repeat. So each page table entry corresponds to 4 bytes. So for 10, 1, whatever bits we have, it requires 4 bytes. And one page can have 16 bytes. So how many page table entries can we have in a page? 4. So we have, let's say this is our first page, PFN equal to 200. In that physical frame number, we have 4 entries. 3 of them are missing. In the next one, PFN equal to 201, we have 1 entry, 3 are missing. PFN equal to 202, all the entries are missing. PFN equal to 203, 2 entries are present. So can anyone guess how we are saving memory now? How we plan to save memory now? Memory of the page table.
So we don't store PFN 202.
So we don't need to store because it doesn't have any valid entry. So this is a linear page table. Now let's look at how we'll do. Sorry, this should have been page table plus page table. So we corresponding to each page, we create. So we just for now let's assume that these are independent pages which exist in the physical frame, physical memory. We have 4 different pages. So a page table, linear page table, is broken down into 4 different pages.
So it should be the next page.
23 should have been in the next one, or just assume 23 was there. Either way is correct. So this is just for illustration. Maybe just put 23 here, because that will lead to more savings for the purposes of illustration. Did everyone get the question? So just assume that 23 is on this position. 0, 1, 2, third position. So we create now what is known as the page directory. So this page directory contains the page frame numbers where the different pages of the page table are stored. Let's say this belongs to the memory address of physical frame number 200. And these are the same as we've seen in the linear page table. So PFN equal to 201, 202, 3, and 4. So we have 4 different pages of a word page table. And one page stores this data structure. which is known as the page directory. Now each entry in the page directory looks at the page number, so pfn equal to 201, looks at a page, physical page, and it sees that if there is any valid entry in that or not. So in this particular page, we have two valid entries. So we say that there exists at least one valid entry in this particular frame number, physical frame number. In 202, we have zero valid entries. So it contains zero number of valid entries here. 203 again doesn't have any valid entry. And 204 has at least one valid entry. So does everyone understand this point? So we create a page directory where each entry corresponds to a physical page, and we maintain a valid bit. This valid is not the same as the valid for the physical page table. This is only telling whether any page exists, so any entry exists or not in that particular page. So and then as Shreyas was saying, so we don't need to. Okay, so before that, this seems kind of wasteful at this point of time, because now we are storing 16 plus 4 entries. 16 entries which present in the physical page table earlier, and 4 additional in this additional data structure. But that's increase the overhead from 16 entries. But that's not the point. We wanted to reduce the number of entries. Now what we say is that for all the page tables, for all the frame numbers for which we don't have any valid PFN corresponding, if we don't have any valid translation, we don't need to store those entries. So we remove the corresponding PFN equal to 202 and PFN equal to 203. Now the number of entries is the total number of entries minus we remove the 8 entries. So 16 plus 4, 21, 8, 12. So we've reduced the number of entries by 4, even though we are using an additional indirection now. Everyone with me at this point of time? Okay, Monica, why can we remove those two physical pages? Good. So there was no valid entry, we can remove that. We don't need to store that extra information. So now, are you in this understanding that this is somewhat related to segmentation, but then it's done in uniform size blocks. And this is fairly similar to how we were doing paging, but this is paging on top of paging. So that's why it's called multi-level paging. In this case, it's two-level paging. This particular data structure is called page directory entry, PD.
So is there any different names that we give to the top pages and the actual pages in the physical memory?
So the last one, so this is typically called PT index, page table index. I'll just come to it in a minute. But as such, again, there is, you just call it by different levels. Directory level 0, 1, 2.
So can the page table sizes be different?
Can the page table sizes be different? No. So we put all of these into page size. So page size, a page can contain 4 entries. So all of them will have 4. You can have lesser, let's say only 2 entries exist, but then that means that those translations don't exist. But you allocate them in fixed page size blocks.
So given that address, how do we access like what bits should we look at the
Yeah, so we'll come to that in a minute. But is this concept clear? Again, you might not at this point of time understand all the details, but at least the concept should be clear that we're trying to plug in the holes by removing those corresponding entries from the linear page table.
So if you have one entry in every PFN, can we merge them into one and delete them?
That sounds like a reasonable approach. It could be a reasonable approach, but then you can have different code segments. So it's not really in your hand that you want to allocate contiguous block of memory or some amount of contiguous memory to code segment. So you don't want the heap to jump into the code segment. That's why what you're saying might not be doable. But if you've noticed, one big advantage that this multi-level paging affords us is, so if you're just using a single page table, linear page table, this has to be PFN 200, 201, 202, and 203. But if you're using multi-level paging, Does this necessarily have to be 201 and 204? Could we use anything else? Great, right? So we now need only a physical page in the physical address space. We don't need a contiguous block also now. So that's a huge advantage now. So you can have them placed anywhere in the memory, as long as you maintain this data structure. So another advantage is that multi-level paging is going to allocate memory proportional to the requirement. So whenever you require more memory, you find another page in the physical address space, you allocate that. And because of that, sparse address spaces are very well supported. And previously, as I was just mentioning previously, we needed 4 MB contiguous space for the page table memory. Now we don't need contiguous memory. And we can place the page table anywhere in memory in multiple pages. So let's look at it as an example now. So let's say we have address space of 16 KB. How many bits? 14 bits. Let's say that the page size is 64 bits. So whenever we mean page size, that also means the offset in some sense. So this would require 2 to the power 6, 64 bytes can be addressed using 6 bits. So the total address required 14 bits. The offset of the page size is 6 bits. What is the BPN? BPN is 8 bits. That's also the number of pages, 256 pages. So 256 pages means 8 bits. So 0000 to 11111111. So basically hex 00 to hex FF is the VPNs, and within each of these VPNs corresponding to each of these pages, we can go from 0 to 60. So corresponding to this virtual address space, we can now create a simple linear page table. We'll have VPN going from 0 to 255, which is hex FF. And let's say that we have, for corresponding to each virtual page number, we have now got an entry of the physical page number. 0 to 10, 1 to 23, 4 to 80, 5 to 89. So we have 1, 2, 3, 4, 5, 6 entries. 1, 2, 3, 4, 5, 6 entries. So does everyone understand at this point of time? Fairly easy, right? Now we want to somehow break this page table into multi-level page, and we want to save some space. So how many entries does this have? It has 6 entries out of total of 255. So how many entries are we basing? 249, right? Okay, so let's look at this page table. Each of these is called a page table entry. Let's say each page table entry is 4 bytes. The total page table size would then be how many bytes? 256 into 1 KB. So the total page table is 1 kilobyte, out of which we wasted 249 by 255 fraction of that page table. So each of this is now a page. So we have different pages in which this page table would be stored. And how many page table entries do we have on a page now? So page table entry is 4 bytes. The page table size is 1 KB. And page size was 64 bytes. So if the page size was 64 bytes, we go back. Address space 16 KB requires 14 bits. Page size is 64 bytes, which corresponds to 6 bits. So just remember this page size in this example is 64 bytes. Number of pages is 2 raised to the power 8, 256. Each page table entry is 4 bytes. How many page table entries can we have in a page? How many page table entries can we have in 64 bytes? 16. So we have 16 entries in a page. So each page contains 16 entries. How many total pages do we have?
Sixteen.
16. Everyone, what 16? Okay, Naman, how did we get 16?
So the page size is 64 bytes,
Bytes.
and the whole table size is 1 KB.
Okay.
So if we divide 1 KB by 64, then we get 16. So we have 16 pages
Right.
in total.
Yeah, good.
So,
The
this 64 bytes means that each page, entry of the page directory is corresponding to this.
page directory, we're not even talking about page directory at this point. We're just looking at the simple linear page table. We're trying to find out the number of entries in each page. So one entry takes 4 bytes. Page size is 64 bytes. So we have 16 entries per page. We have a total of 256 entries.
But number of pages were 256.
Yeah. Number of pages, sorry,
Number of pages were 256.
number of entries is 256.
So each entry also corresponds to a 64 byte page, right?
So each entry, page table entry is 4 bytes.
So no, so the PFN.
So each, yeah, so each of this is also physically allocated the page size, 64 bytes. But we're not as such bothered about the physical address space for now. So we don't get confused by looking at the physical address space. Only look at the page table and try and understand the memory requirements. So we're only trying to reduce the memory overhead of the page table. 16 page table entries per page, total 256 entries in the page table. So we require 16 pages. Everyone with me to this point of time? Sorry?
Each page corresponds to 16 pages. You are trying to say.
Each
Page corresponds to 16 pages. Like I'm not getting why this purple region is 16 page.
Okay, so this is page table entry. Each page table entry is a VPN, PFN corresponding mapping. Now each of this is, so each PFN will have a page size, but let's not bother about that. This is how we are storing this particular data structure in a page. So each take 4 bytes. How many can we place in 64 bytes? 16. So this entire block can be placed in a page. So we have 16 page table entries in a page. We have total 256 entries. So we require 16 pages. Clear? So let's look at these 16 pages now. Let's say that this is one page, this is one page. Again, for illustration, these are not currently of the same size, but just for now, assume that they are. Let's say that this first page actually resides in PFN equal to 100. This last page is actually PFN equal to 101. And the remaining are as such zeros, so they are not even allocated, they don't even reside in the PFN as such. So we have now another data structure which corresponds to PFN. This is basically the page directory. So at each PFN, do we have any valid entries in that particular page? PFN equal to 100, we have at least one valid entry. All of these are empty. PFN equal to 101, we have at least one entry. How many entries do we have here?
16.
Why do we have 16 entries here? So we had total 16 pages. Corresponding to each page, we see that if that page has any valid entry or not. So that is why this is 16 entries. Everyone clear at this point of time? Now how many entries are we using? We're using 16 entries in the page. Sorry. We're using 16 entries in the page directory. We're using how many entries there?
16.
16, and how many are we using here?
16.
So total entries used up. Earlier we were using 256. So it's a huge amount of saving, right? Now, what would happen if the page size was reduced? What happens?
number of wasted pages increases.
Number of wasted pages decreases.
Depends on the size. Yeah, smaller page. You said the page size, right?
Page size reduces. So we'll have
Lesser entries.
lesser entries in a page. That corresponds to lesser wastage within a page. But then if we have lesser entries within a page, we have more entries there. So this is the trade-off that we'll have to look at. So we can take it to the extremes. So if the page table could contain only one page entry, then what happens? Yeah, someone.
It becomes a directory.
So it becomes a useless data structure then, right? It in some sense is a directory itself. So we are storing redundant information. If the page table becomes the entire, if the page size becomes so large that we can get all the entries in it,
Then we don't increase.
There's no pages.
then there is paging, but it's kind of useless. So then again you don't need a directory. But that's going to lead to, so larger page always leads to a lot of fragmentation. Smaller page reduces fragmentation, but then you'll have an overhead. So that's why we need some kind of balance between. Yeah, so this is the final picture that we have. We have a page directory, pfn equal to 100, pfn equal to 101. Let's look at the address space now. So let's say we have 14-bit virtual address space. In this particular case, we have 14 bits. We have a 6-bit offset because we have a page size of 64 bytes. 8-bit DPN, 256 addresses. And now we have 4 bits for the page directory index and 4 bits for the page table index. Why do we have 4-bit PT index, page table index? We have 16 pages. And corresponding to each of these pages, we have a page directory. Clear? Let's do a translation now. So let's say we want to translate hex 3480 virtual address to PA. Okay, Varun, what's the binary for this? You can convert them, individually. So 3 is 0011. F is all times 1. So let's just look at that for now. So hex 3480, 3 corresponds to 0011, F to 1111, and 100000. So if we go back, we said that the first 4 significant bits correspond to the page directory, the next 4 to the page table index, the next 6 to the offset. So the most 4 significant digits here are 1111, which we require. So this is 14 bits, 2 plus 12. So starting from right, the first 4 most significant digits are 1111. That corresponds to F. So that corresponds to the page directory index. The page directory index F. We look at the page directory. Page directory index corresponding to F is 101. So F corresponds to physical frame number 101. Now we go to physical frame number 101, and now we need to find that particular entry in this page table. We go back again here. The next 4 bits tell us the index of that page table. The next 4 bits are 1110. So 1110 is 1111 minus 1. 1111 is F or 15. 15 minus 1 is 14. The second last bit. The second last entry in this particular page table is 55. So it means that this particular address would then correspond to PFN equal to 55. But we're not finished yet. What is left? The offset. The offset is now the last 6 digits, which, because it's a simple example, it's all zeros. So we can create a physical address by taking 55, shifting it by 6 digits, adding the offset. And we get this particular address, x0d0. Yeah? So now you can understand that how complicated or involved any calculation is. So the OS is doing a lot of stuff for us. Okay, so now let's look at, can we go beyond 2 pages? Beyond 2 levels, sorry, not beyond 2 pages, beyond 2 levels in a multi-level paging. Why would we do that?
And paging. So like in the previous example, you had 14 entries which were not useful.
Right.
Like you could reduce that a bit.
So one reason to do that is, so we went to 2-level paging because the what was taking a lot of overhead.
Page table.
Page table was taking a lot of overhead. Now we go to 3-level paging if
Page directory.
page directory is taking up a lot of overhead. So that's the key idea. 30-bit VA space. Let's say that we have a 512 byte page and 4-byte page table entry. So 512 byte page corresponds to 2 to the rest of power. Rest of power 9, which means that we have 9-bit offset, 21-bit DPM.
7 PT.
So we can create a 7-bit PT, but then the page directory is 14 bits. It's huge. So we again do the same operation here, and we get now a 7-bit PD1 and a 7-bit PD2. So again, I want you to work this out yourself in the home or in your hostel. I don't want to spoon feed you at this point in time. Okay, so let's start the next topic, which is swapping. I've pulled some screenshots of the activity monitor, which shows that the virtual memory size of Keynote is 8.5 gigs, of Chrome is 6.4 gigs, and I have few of these processes running. My physical memory has 16 GB now. So what's happening? There's virtualization at play where we are giving more virtual memory than it exists on than the physical memory that I have. So one way to look beyond physical memory is that we are allocating assets more. The other is to look at the concept of that we have a hard disk or SSD also. Can we use that also to increase the scope of virtualization?
What is private?
I don't know. So I was thinking that shared memory would be that, there are some. Yeah, so there could be other processes which, so again, this is the beauty of studying OS. So if I'm using Keynote, what do you think would be the shared memory? What other processes could be using similar memory segments so that Keynote doesn't have to load them? Or let's say instead of Keynote, I'm using PowerPoint, and I'm using some other MS Office product. So if you notice that we have some fairly common features across Word and PowerPoint and Excel, right? Let's say the font chooser. So we don't need to store these corresponding to each of these executables. We can just store one of them into the memory, and we could keep it as a read-only segment. That will be shared memory. At this point in time, I don't know what's the difference between real and private. That's something we should figure out as we. And Chrome requires 6.4 GB. In many cases, the shared memory can also come from other C modules, which say are loaded by other libraries or other executables. Okay, so how many of us have used scikit-learn? How many of us have used it on datasets greater than the RAM? Oh, okay, good. So this is again something known as out-of-core learning. So when you're trying to fit a model which cannot fit into the memory, how do you do that? You break it down into chunks, load a chunk into the memory, and you keep on learning. You keep on iterating the model. So I just wanted to show that stuff beyond physical memory is important, and it's a fairly common use case. So we can go, let's say that this is a virtual address space and this is a physical address space. We now get another entry into the stack. There is assets, no space left. Red means that all of these have been allocated. What can we do now? The trivial solution is kill the process, but that doesn't happen very often these days. Right? What is the other thing we could do? To create more space. By creating more space, whenever you have to create more space, you have to preserve the current memory contents also to somewhere. Now, where can that somewhere be? It has to be SSD hard disk. An important diagram to look at this space is this triangle. So registers are probably the quickest in terms of accesses, but they're also the smallest in terms of the size. So this is a very important trade-off. So whenever you want highest speed, you can only have a small number of them. Cache is quicker than RAM, is quicker than disk, but then you get a lot of disk. Disk is much cheaper, although it's per byte it's fairly cheap. Okay, so when we were using TLB, did the user ever know that whether the PFN or whether the PFN was coming from the TLB or the memory? Does the user know that? No? Why? Because that's the whole goal of abstraction, that's the whole goal of virtualization. That such details are hidden from the user. Does the user ever know if paging is used? Like, before we took the operating system code, did we know that paging was being used? Maybe in the architecture course you did, but otherwise you wouldn't know, right? Common users wouldn't even know. What did it care? Okay, should the user know if the page is coming from the disk or it's coming from the TLB or it's coming from physical address space memory? No, right? This is the goal of virtualization again, another goal of it, that you don't even get to know where exactly the page is coming from. Okay, so how do we ensure that the user doesn't know? So the last time the process used a virtual address, so for the user it seemed that, or for the application it seemed that it was just like memory. The virtual address was just like physical memory. The next time it's going to be used, it also has to behave like it's memory. So it doesn't really care whether it's coming from memory, TLB, disk, as long as the OS provides this abstraction. And in between, whatever is stored has to be preserved. This is HDD, rotation-based HDD, that's RAM. So we have two different components of swapping. One is swap in. So that is moving something from the disk to the memory. And the swap out is moving from the memory to the disk. Okay, if swapping happens well, what do you think are the consequences? If you've created a perfect swapping system. So if you create a perfect swapping system, what is the memory that you can allocate? If the swapping happens well, you can allocate this plus this size. And at the speed of the RAM. So that's the perfect scenario, right? We can allocate both the physical spaces combined together at the speed of the quicker run. But if it happens really bad, then what's the worst case scenario? The space is only of the RAM and speed is of disk. So that's something you never want to do. So these are two extremes which we hopefully not encounter in the next few slides. Okay, so this is the last bit and then we'll continue in the next class. So when does a TLB miss happen? It starts with a virtual page number. It tries to access the cache for the TLB. The page is not found. It's a TLB miss. Simple, right? Then what happens? If there is a TLB miss, the VPN will then try and access the page table entry which exists in the physical memory. If that corresponding entry does not exist, it's actually called a page fault. So it means that a VPN exists, but that page does not exist in the RAM. That is a page fault. That page is actually present in the disk. Okay, so interestingly, every page fault will be preceded by a TLB miss. Everyone got that? Or no? But is the vice versa true? For every TLB miss, will we have a page fault? No, right? Because the page could reside in the RAM or in the physical memory. So with this, let's end today's lecture.